So we were talking about what happens to white dwarf stars, and we said that if it gets above 1.4 solar masses, then degenerate electron pressure cannot sustain it, and it just continues to collapse. So how far does it collapse? Well, as it starts collapsing, then the atoms get closer and closer together, nuclei get closer and closer together, because what happens is that you have enough energy from the gravitational energy, you can start this thing just squeezing closer and closer together. And so what happens is that it squeezes until all the nuclei are so close together, they're so hot that they start bumping into each other and fusing. At that point, what happens is you get runaway fusion inside the white dwarf. And so you start fusing things that otherwise would be not fusing. If you remember, when we talked about the other fusion reactions that go on in massive stars, we said that the carbon will fuse into neon. The neon will fuse, and you keep going through the process, fusing all kind of other things. And what happens is that all this stuff starts fusing all at once in this incredibly small volume, but it's a degenerate system, so the fusion releases more energy, which makes more fusion happen. And so it runs absolutely wild. In fact, you start fusing beyond necessarily what you would normally get. You can actually fuse beyond iron because you've got the excess energy to do that. You don't need to release energy to support everything. So you start fusing and making a whole bunch of things in the periodic table that normally you would not be making. All this energy, though, is released all at once in a very short time period. And so within seconds, you're releasing as much energy as you would normally release in the entire life of a star. And so in that case, all this energy releasing actually destroys the electron degeneracy. The excess energy, instead of making it collapse, actually makes it expand. And so the entire white dwarf suddenly explodes in a giant, furious, huge explosion. We call that a carbon detonation supernova, even though it might actually be neon it's detonating. So all that would take is exceeding the Chandrasekhar limit. So what would make a white dwarf star exceed the Chandrasekhar limit? Well, one way of doing it might be if you had a white dwarf star that was real close to the Chandrasekhar limit and was accreting stuff. But that process is actually not overwhelmingly efficient. Because it would be very difficult to create enough stuff, because if you're very close to the Chandrasekhar limit, just adding a little bit of stuff creates a little mini nova, which blows stuff away, which slows down the process of adding stuff, and eventually the other star that's dumping stuff onto the white dwarf would eventually stop doing it because it would die itself. And so while that process could work, another possibility would be if you had two white dwarf stars, and you had two white dwarf stars and they were orbiting each other and spiraling in closer together. If they merge, each star would be less than the Chandrasekhar limit, but when they merge, the combination would be a white dwarf star above the Chandrasekhar limit. And in that case, you'd trigger this collapse. So that's another way that term supernova actually came from Walter Baade, who was working with Fritz Zwicky and at the Mount Wilson Observatory at the time. And so that was we talked about Baade before when he was at Mount Wilson. And so they were studying these novae, or sudden new stars that appeared, and Baade realized that, and Zwicky, that some of these things were too bright, much too bright, and they would exceed the Eddington limit by far, and that there'd be no possibility of a star surviving. And so that's when they came to the realization that you would have this thing that would be an exploding star. And so in German, they called it a grand nova. That translated into English as a supernova. And that's the term that we started using for this kind of explosive event. They tracked down a potential supernova remnant in the Crab Nebula. This was an explosion that happened in the year 1054. People recorded seeing bright object in the sky. It would cast shadows at night, and you could actually read by the light of it at night. It was really bright explosion. From thousands of light years away. And when you look in that direction, you see this expanding cloud of gas, and that's the remnant of the outer parts of a star that blew up. Now, I should point out the star that blew up in this case was almost certainly not a white dwarf that exceeded the Chandrasekhar limit. This is another type of way of making supernova, made this particular remnant right here. Native Americans recorded that supernova in drawings that they made at that time. And there's a image of the Crab Nebula, M1, Messier number 1. And there's actually interesting indications. It's Messier number 1, first thing on Messier's list. And so you'd think the first thing on his list that he had put would be one of the brighter things, but M1's not one of the brighter things. It's not one of the brightest things. And so there's some indications it's actually been gradually getting dimmer a little bit, perhaps since Messier saw it. And here's a image right here and another image. So we got two images that are taken about 30 years apart. And if you look carefully, you can see some of the little tendrils of gas up here relative to stars in the area. And so you would see these little tendrils of gas slowly moving. And so you can sort of see again, little blobs of gas slowly moving past the stars. So one thing you could do is actually measure it at one size and then compare it to the other size. And it's 30 years apart, figure out how far it moved, and run backwards to figure out when it exploded. And you find out it exploded about 1,000 years ago. It's not all moving the same speed, so you're not going to get exactly 1054, but you'll get, millennia ago that this thing exploded. And so that does match the records. There are other supernova remnants that are out there. You can see them in X-rays and in radio waves. Sometimes they did not. There's no indication of when they happen in terms of visual records. Some of them are sitting behind other interstellar medium that would have blocked the view of them. And so there are a bunch of them out there. Cassiopeia A is one of these that does that. And if you look at different spectral lines, so in other words, the different elements give off different radio waves, and you can look at look at it in different spectral regimes, and you can actually see, that it's actually got some of these other elements that you normally would not be forming in a just an ordinary star like the sun. And so many of the elements that make up Earth are formed in a supernova explosion. The blast is so powerful, it shocks the interstellar medium nearby, pushing it outwards. You get the shock wave goes through there. And that's the interesting thing, that shock wave of a dying star can actually generate new stars forming, because now you're going to compress the interstellar medium, and that can exceed the Jeans criterion and start making new stars. Veil Nebula, this is another very pretty one. For many, many decades, this has been a very pretty sort of thing that amateur astrophotographers would like to take pictures of. It's difficult to do, it's dim, and it's very spread out. And so this is kind of like a challenge object or an ultimate sort of thing that amateur astronomers, amateur astrophotographers would try to take pictures of and share. Hey, look what I did with the Veil Nebula. Supernovae are named. The very first one discovered in a constellation is called A, and then B, and so forth. Not in a constellation, but in a year rather. Supernova. The first supernova in 1987 would be called 1987A. The second one's 1987B. Third one 1987C. First one in 2011 would be 2011A, then 2011B. First one in 2020 would be 2020A, then 2020B. In the old days, you only found a one or two supernovae per year, and so that was fine. And then you got up to where you got, a dozen supernovae per year, and then 20 or so supernovae per year, and finally you get to the point where you filled the alphabet. So they went back and they just started doing AA, AB, AC, and so forth. So right here is a finder chart put out by the AAVSO for a supernova in the constellation Sextans. And in fact, it's in a galaxy, NGC 3169, which is in the constellation Sextans. And so the supernova was 2003 CG, which makes it the 82nd supernova discovered in 2003. Today, there are automated telescopes that just look at the sky, take pictures of the same part of the sky on a regular basis, and computers compare the images to what were there before, and so you can actually find when new stars appear. So that'd be okay. Should point out that the carbon detonation supernova that we talked about here as our introduction to supernovae is actually not the most common kind of supernova. The most common kind of supernova actually comes from the core of a massive star collapsing. I started off with the type I did because that just seemed to naturally follow with our discussion of white dwarf stars. So our next topic is going to be how really big stars die. And by big, I mean something bigger than 8 solar masses. If it's less than 8 solar masses, then it's going to produce a neutron star as a stellar remnant. If it's bigger than 8 solar masses, though, the core is going to get bigger than 1.4 solar masses, and so it's going to collapse. When it collapses, then that's going to release the energy in the core as it's collapsing. It's very similar to the way carbon detonation supernova collapses, except you don't get quite as much nuclear fusion in the core. But you do get nuclear fusion all around the core, and so and the release of energy then blows up the rest of the star, and so the core becomes something else, and the outer parts of the star blow out. Now remember, the star is over 8 solar masses, and so the core has to be about 1.4 solar masses. So most of the mass of the star gets blown away. And that gets blown away in the form of a supernova remnant. And so that would be our very next topic of study.